Hi, this is Miss Bennett again. We're going to be talking about equilibrium. We did already give a definition of this back in the first part of the notes, but let's talk about it again. Up until now, we have been talking about how reactants yields products, and that's the only way we have talked about it. But keep in mind, this reaction will go in both directions. The forward reaction is going from reactants to products. The reaction is going from products to reactants. And both of these processes go on at the same exact time, and when the rate of reactants becoming products and products becoming reactants are equal to each other, that is when we go into equilibrium. This is not the symbol for equilibrium. It is arrows, one on top of the other. You can draw a half arrow or a full arrow to indicate equilibrium. And equilibrium, once again, is where the forward reaction rate equals the reverse reaction rate. Concentrations of the products and reactants remain the same. In talking about equilibrium, we do have to talk about Lacheys Principle. And what that says is if a chemical system is at equilibrium and there is a change in concentration, temperature, or total pressure, the equilibrium will shift in order to keep the system in equilibrium so that we can minimize that change. So if you have a change like temperature, concentration, and total pressure, the reaction will actually shift in the direction. And what we do is we think of it as a seesaw or a teeter-totter is what you guys may have called it in elementary school. But if a teeter-totter is straight across, this is the equilibrium position. If you've got something, a teeter-totter that's like this, like in this example here, we're out of equilibrium. Or up here, out of equilibrium. We want it straight across. This is going to represent our equilibrium reaction. So let's talk about concentration first. Okay, if you increase the concentration of HI, so we've got a reaction here, we've got a synthesis reaction here, and we've got the reactants of H2 and I2 to give us HI. So what it's asking us is if we increased, so here's our teeter-totter again, and right now it's in equilibrium, that should be straight across. If we added more HI to this reaction, what's going to happen to our seesaw? Well, it's going to fall because we have more added to this side. Well, in order to get back to equilibrium, according to Le Chatelier, it's got to shift in the opposite direction to get it back to a straight teeter-totter. So this is going to shift the reaction to the left or towards the reactants. If you increase the concentration of H2, so here's my teeter-totter. I increase the reaction on this side, it's going to make my teeter-totter go down on the left-hand side. So in order to get it back to equilibrium, it has to shift in the opposite direction, so it'll have to shift to the right or towards the products. What if you decrease both concentrations? So what if I decrease an H and an HI at the same rate? What direction will it shift? It's not going to have a shift because it will still mean that the concentrations will be equal. If we increased this one and increased this one at the same rate, there is no shift. It's from one side to the other where it becomes unbalanced. All right, so if we change the temperature, remember we have to think of temperature or heat energy as a reactant or a product. And remember, just to review, if it is exothermic, it is a product. If it is endothermic, it is a reactant. So in this case, you've seen these reactions before. This is ammonium nitrate plus water plus 500 joules and gives us ammonium hydroxide and nitric acid. If I increase, so here's my teeter-totter, reaction in equilibrium. If I increase the amount of energy on this side, which means I'm adding to this side of the teeter-totter, that will cause my teeter-totter to do this, which means then if I increase temp, this reaction would have to shift to the right. If I decreased the temperature, so if I start off in equilibrium and I took something off of this side, that means my teeter-totter is going to fall this way, which means it would have to shift left to get back to equilibrium. If I take the cellular respiration, once again, if we increase the temperature here, increase the amount of energy. So if I increase the amount of energy, my teeter-totter looks, or it's on this side, it's exothermic. I increase energy, which means I add to this side. My teeter-totter is going to fall to that side. In order to shift it back, it has to go back in the opposite direction. So it's going to shift to the left or towards the reactants. If I decrease temperature, which means if my teeter-totter starts off in equilibrium, I take something off of this side, my teeter-totter will fall this direction, which means it would have to shift right or towards the products. Pressure. You cannot do the teeter-totter example with the pressure. If you increase pressure, you go towards the fewest molecules. If you decrease pressure, you go towards the most molecules in a reaction. And the way we get the molecules from the reaction is we look at the balanced equation and take those coefficients. So let's do an example of that one. So if I start off with this one, and this arrow here should be like this, okay? I've got two NOCLs over here, two NOs, and one Cl2 over here. If we increase pressure, it wants to know what this thing would do. Well, if we go back, if we increase pressure, it goes towards the fewest molecules. So if I count molecules, over here, I've got 2 molecules on the reactant side. Over here, I've got 2, and remember if there's not a number, that's a 1, so I've got a total of 3 over here. So if I'm increasing pressure and it goes toward the side with the fewest molecules, it's going to shift left. If I decrease pressure, it goes towards the most molecules, so it should shift to the right or towards the products. Now, if I increase pressure here, first thing I've got to do is count molecules. Well, here I've got 1, 2 molecules. Here I've got 1, 2 molecules. There is no fewer or most, since they're exactly the same number of molecules on both sides. Increasing or decreasing the pressure, there is no shift for equilibrium. All right, so if we're looking at this example here, okay, I'm going to switch to page 14 in your book. So I'm going back to your book, and this is page 14. So page 14, that we've been given this reaction where we've got some energy, hydrogen and iodine, is going to give us that HI. So we are back to that same synthesis reaction. Kilocalories here is just another energy unit, just like joules is. So that's going to be your energy or your thermal energy there. So if we take a look at this first one, if we add H2, so adding H2 means on our teeter-totter, we're adding here, which means it's going to cause it to fall to the left, which means it would have to shift to the right. If it shifts to the right, then that tells me that the amount of HI, because my arrow is pointing in that direction, is going to increase, and the amount of my I2 is going to decrease. If I add I2, once again, I'm adding more to this reactant side, which means it's going to fall in this direction. So in order to get back to equilibrium, it has to shift to the right. If it shifts to the right again, the amount of H2 is going to decrease. The amount of HI is going to increase. Now, if I add HI this time, so I'm going to add on this side. It's going to cause my teeter-totter to fall this way, so in order to shift back to equilibrium according to Le Chatelier, it's going to have to shift to the left. If it shifts to the left, then we're going to get more HI and more I2. All right, if we take out hydrogen, so in other words, we're taking something out. We're taking someone off of this side of the teeter-totter, which is going to cause my teeter-totter to shift or to fall in this direction, which means it would have to shift to the left. If it shifts to the left, that means the amount of I2 increases, while the amount of H2 being at the tail of that arrow will decrease. If I remove I2 being on the left side, if I take that out, once again it's going to fall to the right, so it would have to shift to the left to get back to equilibrium. And if it is shifting left, that means H2 will increase and HI decreases. Now if I remove HI, that means my teeter-totter is going to fall to the left, which means if it falls to the left, it's got to shift to the right to get back to equilibrium. If it shifts to the right, that means the amount of H2 is going to decrease, and so will HI. Or excuse me, I'm sorry, so will I2. All right, if we increase temperature, we have to think of temperature as a reactant or a product, and in this case it is on the reactant side. We're going to increase, we're going to increase temperature. So we're adding more to this side, which would cause my teeter-totter to fall in that direction, which means it would have to shift to the right. If it is shifting to the right, H2 decreases, I2 decreases, and HI increases. If I decrease temperature, which means I'm taking something off of this side, my teeter-totter is going to fall to the right, which means it would have to shift to the left to get back to equilibrium. If it shifts to the left to get back to equilibrium, H will increase. We're going towards it. I will increase, and HI will decrease. All right, remember with pressure, we cannot use our teeter-totter example. We have to count molecules, so let's do that. If we increase pressure, so if we look here, we've got 2 molecules. Over here, we've got 2 molecules. They are exactly the same as far as molecules, 2 and 2, so there means there is no